Hello everyone. So this is the next video on linear algebra. So in the last class we discussed the definition of the basis and few results on the basis and how the linear dependence and independence are related, and we discussed some important results. So there are some results on the dimension of the subspaces. Already we know what are subspaces are. So we start with the result 1, which says if W is a subspace of the vector space V over the field F, then dimension of W is less than dimension of V. In the sense, you see, W is a subspace of V. So dimension of W will be less than or equals to dimension of V. When it will be equals to W, then we say you can just stretch it out up to V. In the sense, V will be nothing but W itself. So every vector space is a subspace of itself. So this dimension of W is less than or equals to dimension of V. One thing. Then if V of F is finite dimensional, then the basis, that is of this basis of the subspace, can be extended into the vector space. Suppose let us assume I have the basis for beta 1 is the basis for W, which is a subspace of V. Then I can extend, if suppose V is finite dimensional, I can extend the basis B1 to V. Already we know extension theorem, basis extension theorem, which says if I have linearly independent vectors, I can make them to match with basis. I can extend them to the basis. For example, if I add r to the power 4 and I have two linearly independent vectors E1, E2, then I can add E3 and E4 for this to become the basis for R4. This idea is clear? Okay. Then the third one is, if V of F as the basis V1, V2, etc. up to Vn, then given any vector in the vector space V can be uniquely expressed. So if I have one vector, then the representation of this is unique. How the representation is a linear combination of this basis elements V1, V2, etc. up to Vn. It will be unique. Is the idea is clear? I can represent this V by the linear combination of this set, and the representation is unique. Idea is clear? Okay, this fourth one is dimension of W1 plus W2. This is nothing but the linear sum, W1 plus W2. Already we discussed what is the linear sum. So dimension of W1 plus W2 is dimension of W1, dimension of W2 minus W1, dimension of W1 intersection W2. The idea is this here. See, we already know n of A union B is n of A plus n of B minus n of A intersection B. The set theory works here, but still, once we are discussing the subspaces, union of two subspaces need not be subspace. Suppose A and B are any two subspaces of the vector space. A intersection B will be the subspace, but A union B will not be the subspace. When it will be subspace, you can add them. So that's why dimension of W1 plus W2. You can speak about the dimension if it is a vector space, but you cannot say union will be a subspace always. It will be a subspace if one is contained in the other. That's why this notation is used, W1 plus W2. That is the key idea here. Kindly try to remember in that way. Okay, this is an fifth one is important in the point of examination. What is the option that they ask? You see here V is a vector space of matrices over the real entries. Then what is the dimension of the vector spaces of these following categories? So I have a square matrix M cross N matrices whose sum of the first row is 0. First row is 0 means, for example, 3 cross 3, let us assume A, B, C, D, E, F, G, H, I are the elements. So first column is 0 means, first row is 0 means what? Sum of first row a plus b plus c is equals to 0. That means a plus b is equals to minus c. If I know a and b, I can write what is c. Third one I can write using these two. That means this depends on a and b. So if you don't give me c also, it's okay, no issues. Condition is given, add them and take the minus of that sum. So if you don't give me c, still I can write c. That means how many elements are needed? 1, 2, 3, 4, 5, 6, 7, 8. That is m into n is 9 elements are there. 9 minus 1, that is 8. Idea is clear? Likewise, if the sum of first column is 0, still a plus d is minus g. So if any one of the sum of the any one of the row is 0 means you can write, you can just say the mn minus 1. Then sum of each row is 0. Same idea. Each row is 0 means a plus b is minus c, d plus e is minus f, g plus h is minus I. So these three elements are not needed. You can write them by a plus b, you can write them by d plus e, and you can write the third one by g plus h. So in the sense it is mn minus m elements. This idea is clear because m rows, n columns. Then if sum of each column is 0, then it is mn minus n. How many columns are there? That much elements are not needed. Mn minus n. If sum of each row and each column is 0, that means, see, idea will be this here now. A, B, C, D, E, F, G, H, I. A plus B is minus C, is minus F, G plus H is minus I. Similarly, A plus D will be minus G because sum of each row and each column is 0. Then again, B plus E is minus H and B plus E is minus H, C plus F, it is minus I. That means if I want to write this element, there are two choices, G plus H or else C plus F. So Mn, you just say what is the dimension, then take this three elements are excluded. Again these three elements are excluded. So how many times I repeated? I repeated one element. This idea is clear. I excluded three columns, that is nothing but G, H, I, and the elements of the rows, that is C, F and I. So I counted I twice. That's why I need to add them once. This idea is clear. Don't write it as mn minus m minus n. Plus 1 you need to add because you already counted I twice. ಎರಡು ಸಲ ಕೌಂಟ್ ಮಾಡಿಬಿಟ್ಟಿದ್ದೀರಾ ಐನ. ಸೊ ಅದನ್ನು ಒಂದು ಎರರ್ ಹೋಗಬೇಕು ಅಂದರೆ ಪ್ಲಸ್ 1 ಆ್ಯಡ್ ಮಾಡ್ಕೋಬೇಕು. Simple. Try to just think about in 3 cross 3 or else 3 cross 4. Don't go beyond 4 cross 4. Okay. Then it's a square matrix, n cross n matrix, whose all non-diagonal entries are 0. Non-diagonal entries are 0 means what? So you have only all are 0 here. Now what is the situation? So here I have elements n cross n. So a11, a1, a22, a33 likewise. So it must have n elements. Dimension must have n elements. N cross n scalar matrix. Scalar matrix means it's a diagonal matrix where these elements are same. That is called scalar. So how many elements are needed? Only one element is needed. So n cross n tridiagonal matrix. What is this tridiagonal matrix? Tridiagonal matrix means, see, if I have a matrix a11, a12, a1n, a21, a22, a2n, a23, a31, a32, a3n, an1, an2, ann. So this is diagonal and this is super diagonal and this is subdiagonal. So these three are called tridiagonal. Above the diagonal, below the diagonal. If you include them, it is called tridiagonal. So he is giving the condition for tridiagonal matrix. Only these entries are there. All the remaining entries are 0. This idea is clear. So how many elements are there? It's an n cross n matrix. So first I have here n cross n. That is n elements are here in the diagonal. Above the diagonal, how many elements are there? N minus 1 will be there. Below the diagonal, how many elements will be there? N minus 1 will be there. Add them. 3n minus 2. That is given here. Clear? So these terms must be understood. Yes. N cross n symmetric matrices. See, symmetric matrices means, we'll just try to give the example for symmetric. Skew symmetric will follow in the same way. So here I have, let me give for 3 cross 3, that would be better. 1 is here. Let me say 2 and 3. So I have A here and minus A must be, sorry, A must be here since it is symmetric. If B is here, B must be here. C is here, C must be here. Idea is clear. So how many elements are needed to write this? So these 3 elements is needed, right? Then how many elements are needed? AC is already given here, so 2 elements are needed. B, 1 element is needed. This B is repeated here, so you can just count only this. Illa melgadanadru count madi, illa kelgadanadru count madi. In the sense, so it is 1 plus 2 plus 3 for 3 cross 3. So it is nothing but 6. If I have 4 cross 4, it will be 1 plus 2 plus 3 plus 4. Howda? ಸ್ವಲ್ಪ ಅರ್ಥ ಮಾಡ್ಕೋಬೇಕು. That means n entries will be here. N minus 1 entries will be here. Keep on decrease ಆಗ್ತಾ ಹೋಗುತ್ತೆ ಅದು. Going on and on, 1 element will be here. So how many elements are needed? 1 plus 2 plus 3 etc. up to n, sum of natural numbers. It is nothing but n into n plus 1 by 2. That's what I had given here. Skew symmetric n into n minus 1 by 2 ಆಗುತ್ತೆ. Just check it once why it is. Similar way. But here this term will not be there because it is 0. ಅರ್ಥ ಆಗುತ್ತಾ? This term will not be there. So you need to have only 1 plus 2 plus 3 etc. up to n minus 1. Getting my point? So this won't be there because all these are 0. Skew symmetric means 1, 2 etc. up to n minus 1. So what is sum of natural numbers up to n minus 1? N minus 1 into n minus 1 plus 1 by 2, which is nothing but n minus 1 into n by 2. That is n into n minus 1 by 2. Sum of upper triangular or lower triangular, it is n into n plus 1 by 2. Check it why it is. See, if I say upper triangular, we will say this must be non-zero and this and all are 0. Lower. So we need to concentrate on the lower entries. This can be anything. This can be 0 or non-zero. It's okay. But this must be, what else the lower entry is there, it must be 0. So once we say upper triangular, we must concentrate on the lower, that is to the left of the principal diagonal. It must contain 0. Then we say that it is upper triangular. Illi enadru irbodu, either it is 0 or non-zero. But here it must be 0. Similarly for lower triangular, you must concentrate on upper triangular entries. Here you must concentrate. Here it can be anything, but here it must be 0 for lower triangular. So n cross n diagonal matrix. See, for diagonal matrix we want n elements with trace equals to 0. One condition is given. What is the trace? Trace means sum of diagonal elements a11, a12 plus etc. a22, a must be 0. That means one condition you need to remove. That is, in place of the trace, see, 3 cross 3 ತೊಗೊಂಬಿಡಿ, ಅರ್ಥ ಆಗ್ಬಿಡುತ್ತೆ. If you take 3 cross 3 you can understand. For example, n cross n diagonal matrix. Diagonal matrix ಅಂದರೆ you must have only diagonal entries. For example, I will have, let me say 9 3 minus 1 ಅಥವಾ a b c ಅಂದ್ಬಿಡಿ, that would be better. So all are 0, that is the diagonal matrix. Diagonal matrix, how many elements you want? 3 elements. So I wrote 3 first. But he is telling trace is 0. Trace 0 means what? A plus B plus C is 0. That implies A plus B is minus C. That means if you know A and B, you can write what is C. That means this fellow is not needed. If he is not in picture also, it's okay. You can write C because you know what is C is. C is, you take the sum of A plus B and take the negation of it. Minus of A plus B is C. So if you know A and B, you can write what is C. That means you need to have only 2 elements. 1 element is not needed. Not needed, no. So I will take minus 1. So it is 2. So that is the idea. What else? How it is going on? N cross n null matrix. Null matrix means it contains 0. So everything 0 means its dimension is 0. Then the only subspace of R over R is there is 0 subspace and R. In the sense, see, R is a vector space over R. What is the dimension? Dimension is 1. So already we know if it is if W is a subspace, dimension of W is less than dimension of V. In the sense, dimension of W is less than, what is the dimension of V? If it is V and it is F, dimension of V over F is 1. Dimension of V is less than or equals to 1 means, what else it implies? Dimension of W, either it is 0 or, if it is 0, it is 0 subspace. If it is 1, it is nothing but V itself. That's what I had stressed here. The only subspace of R over R is either 0 subspace or V itself. V is nothing but R itself. The subspace of R square is either, see, subspace of R square over R, it contains, because dimension is 2, right? Either it can be 0 or it can be 1 or else 2. 0 means 0 subspace. 1 means the straight lines that passes through the origin, or else the scalar multiples of some fixed vectors in R square. That is the thing. Fixed vector means this is fixed vector. B is fixed. A into x plus b. This idea is clear? Or else you say in this way, which passes through the origin. It must contain the straight line that passing through the origin. 2 means it is R square. Idea is clear? Okay. That's what space consisting of all scalar multiples of some fixed vectors. Let me fix a vector V and scalar is A. Instead of V, take V is equals to X. That is Y is equals to AX, which is nothing but the straight lines which passes through the origin. If something is given, for example, Y is equals to some V is equals to AX plus 3, whether it is the subspace of R square. No, because if I plug in X equals to 0, it is 3. It won't pass through the origin. Its Y intercept is 3. Idea is clear? So that's the key role here, you need to understand. Then if V is an n-dimensional vector space over the field F, then cardinality of F is P, in the sense you take field to be ZP, because ZP is a field. Idea is clear? Then the number of elements of V of F is P to the power n. This is easy, but you need to have one result in your mind. See, what else I am stressing here is, V is an vector space over the field F. V is an vector space over the field F, with the idea this is nothing but let me consider Zp itself, and the dimension is n. Then what is the cardinality of V over F? You can find how many elements are there in this. How it is possible? See, what is the dimension? N. So let us assume V1, V2, V3, Vn is the basis. Since the dimension is n, this is the basis. So given any vector V belongs to that vector space, already we know this can be written uniquely by this linear combination, by the result what else we had observed. Given any vector in that vector space V, it can be expressed uniquely by V1, V2, etc. up to Vn. So V is nothing but some scalar into V1, some scalar into V2. I will write that scalar what it is, plus some scalar into V3, some scalar into Vn. Hope you are agreeing with me. Now what is this scalar? Scalar is from the field. How many elements are there in the field? P elements are there, Zp. So you have P choices for this. Similarly, how many elements you can take for this? P choices. So here P choices, here P choices. So totally you have P cross P n times. So P to the power n. And since you may ask me, sir, if some elements are equal, then the dimension cannot be P to the power n. No. If I say an element belongs to this, it can be uniquely expressed by the linear combination of this. That means for every linear combination there is an unique element. So how many linear combination possible? P to the power n. So how many element does it has? It has P to the power n elements. There is an 1-1 correspondence. So P to the power n elements will be there. That's the idea here. So here this ninth one is recursively asked. How many basis elements are there for the same scenario? V is a vector space over the field Zp of dimension n. How many basis elements will be there? See, first of all, this is the formula. But how to think about this formula? First thing is P to the power n minus 1. Why P to the power n minus 1 is the first question. Because how many elements are there in this vector space? P to the power n elements will be there. That's what we had observed from the result 8. Minus 1. Yak ondun kalibeku. Why we need to subtract 1 here? Because 0 element is there. It cannot be in the basis. So I will take minus 1. But then why P to the power n minus P? Because if alpha is in vector space, then I can find the scalar multiple of this. How many scalars are there? Which is, see, if I say instead of alpha I will say some V itself, V1. V1 is a vector in the vector space V. I can find scalar multiples of this. How many scalar multiples I can find? How many such scalars are there? That much scalar multiples I can find. How many scalar multiples are there from the field Zp? That means it has 0, 1 bar, 2 bar. Likewise P minus 1 bar. That means this scalar can be 0, then 1 into V1, this thing, then 2 into V1. Likewise, how many? So P minus 1 into V1. That means how many linearly dependent fellows are there? P linearly dependent. So in this P to the power n, I subtracted first 0 vector, then I subtracted P to the power n. Sorry, P vectors, because these P vectors are linearly dependent. So next consider V2 belongs to vector space. So how many fellows will be there here? Similar to this, P fellows will be there. Then why you subtracted P square, sir? I subtracted P square because V2 and V1, linear combination of this alpha into V1 plus beta into V2. Here I have P choices, here I have P choices. So how many? P into P square. So P square. Similarly Pn minus P cube. So it goes on and on, Pn minus p to the power n minus 1 by n factorial. Why this n factorial? Because it has ordered basis. Once you are subtracting, it has all the ordered basis, but you want only the basis. If you want only the basis, you divide by n factorial. Idea is clear? So that must be understood. How many ordered bases will be there? Ordered basis means you don't need to divide by n factorial. Just say p to the power n minus 1, p to the power n minus p, etc. p to the power n minus p to the power n minus 1. Third one, see, this you must remember. Number of subspaces of dimension r. See, the numerator is same up to this, the last term, p to the power n minus 1, p to the power n minus p, etc. p to the power n, instead of p to the power n minus 1, you substitute r minus 1. Idea is clear? So here I had n minus 1, but here you have r minus 1. That is the difference in the numerator. Coming to the denominator, in place of n, wherever you have n, replace it by r. That's all. So that will give the number of subspaces of dimension r. Once we solve some assignment questions, we will be exactly knowing why all these things are used. Ninth one is important. So this covers the concept on basis of subspaces. So later on we can just move on to some linear sum and direct sum of the given two subspaces. Then we can solve some problems and we can conclude the first chapter of linear algebra. Thank you.